In physics, a state of matter is one of the distinct forms that matter takes on. 4 states of matter observable in everyday life: solid, liquid, gas, and plasma. Many other states are known to exist only in extreme situations, such as Bose-Einstein condensates, neutron degenerate matter and quark-gluon plasma, which occur in situations of extreme cold, extreme density and extremely high energy color-charged matter respectively. Some other states are believed to be possible but remain theoretical for now. For a complete list of all exotic states of matter, see the list of states of matter. Historically, the distinction is made based on qualitative differences in properties. Matter in the solid state maintains a fixed volume and shape, with component particles close together and fixed into place. Matter in the liquid state maintains a fixed volume, but has a variable shape that adapts to fit its container. Its particles are still close together but move freely. Matter in the gaseous state has both variable volume and shape, adapting both to fit its container. Its particles are neither close together nor fixed in place. Matter in the plasma state has variable volume and shape, but as well as neutral atoms, it contains a significant number of ions and electrons, both of which can move around freely. Plasma is the most common form of visible matter in the universe. The term phase is sometimes used as a synonym for state of matter, but a system can contain several immiscible phases of the same state of matter. For further discussion of the difference between the two terms, the 4 fundamental states. Solid. In a solid, the particles are closely packed together. The forces between particles are strong so that the particles cannot move freely but can only vibrate. As a result, a solid has a stable, definite shape, and a definite volume. Solids can only change their shape by force, as when broken or cut. In crystalline solids, the particles are packed in a regularly ordered, repeating pattern. There are various different crystal structures, and the same substance can have more than one structure. For example, iron has a body-centered cubic structure at temperatures below 912 degrees Celsius, and a face-centered cubic structure between 912 and 1394 degrees Celsius. Ice has 15 known crystal structures, or 15 solid phases, which exist at various temperatures and pressures. Glass is another non-crystalline, amorphous solids without long-range order are not thermal equilibrium ground states, therefore they are described below as non-classical states of matter. Solids can be transformed into liquids by melting, and liquids can be transformed into solids by freezing. A liquid is a nearly incompressible fluid that conforms to the shape of its container but retains a constant volume independent of pressure. The volume is definite if the temperature and pressure are constant. When a solid is heated above its melting point, it becomes liquid, given that the pressure is higher than the triple point of the substance. Intermolecular forces are still important, but the molecules have enough energy to move relative to each other and the structure is mobile. This means that the shape of a liquid is not definite but is determined by its container. The volume is usually greater than that of the corresponding solid, the best known exception being water, H2O. The highest temperature at which a given liquid can exist is its critical temperature. A gas is a compressible fluid. Not only will a gas conform to the shape of its container but it will also expand to fill the container. In a gas, the molecules have enough kinetic energy so that the effect of intermolecular forces is small, and the typical distance between neighboring molecules is much greater than the molecular size. A gas has no definite shape or volume, but occupies the entire container in which it is confined. A liquid may be converted to a gas by heating at constant pressure to the boiling point, or else by reducing the pressure at constant temperature. At temperatures below its critical temperature, a gas is also called a vapor, and can be liquefied by compression alone without cooling. A vapor can exist in equilibrium with a liquid, in which case the gas pressure equals the vapor pressure of the liquid. A supercritical fluid is a gas whose temperature and pressure are above the critical temperature and critical pressure respectively. In this state, the distinction between liquid and gas disappears. A supercritical fluid has the physical properties of a gas, but its high density confers solvent properties in some cases, which leads to useful applications. For example, supercritical carbon dioxide is used to extract caffeine in the manufacture of decaffeinated coffee. Plasma. Like a gas, plasma does not have definite shape or volume. Unlike gases, plasmas are electrically conductive, produce magnetic fields and electric currents, and respond strongly to electromagnetic forces. Positively charged nuclei swim in a sea of freely moving dissociated electrons, similar to the way such charges exist in conductive metal. In fact, it is this electron sea that allows matter in the plasma state to conduct electricity. The plasma state is often misunderstood, but it is actually quite common on Earth, and the majority of people observe it on a regular basis without even realizing it. Lightning, electric sparks, fluorescent lights, neon lights, plasma televisions, some types of flame and the stars are all examples of illuminated matter in the plasma state. A gas is usually converted to a plasma in one of two ways, either from a huge voltage difference between 2 points, or by exposing it to extremely high temperatures. Heating matter to high temperatures causes electrons to leave the atoms, resulting in the presence of free electrons. At very high temperatures, such as those present in stars, it is assumed that essentially all electrons are free, and that a very high-energy plasma is essentially bare nuclei swimming in a sea of electrons. Phase transitions. A state of matter is also characterized by phase transitions. A phase transition indicates a change in structure and can be recognized by an abrupt change in properties. A distinct state of matter can be defined as any set of states distinguished from any other set of states by a phase transition. Water can be said to have several distinct solid states. The appearance of superconductivity is associated with a phase transition, so there are superconductive states. Likewise, ferromagnetic states are demarcated by phase transitions and have distinctive properties. When the change of state occurs in stages, the intermediate steps are called mesophases. Such phases have been exploited by the introduction of liquid crystal technology. The state or phase of a given set of matter can change depending on pressure and temperature conditions, transitioning to other phases as these conditions change to favor their existence. For example, solid transitions to liquid with an increase in temperature. Near absolute zero, a substance exists as a solid. As heat is added to this substance, it melts into a liquid at its melting point, boils into a gas at its boiling point, and if heated high enough would enter a plasma state in which the electrons are so energized that they leave their parent atoms. Forms of matter that are not composed of molecules and are organized by different forces can also be considered different states of matter. Superfluids and the quark-gluon plasma are examples. In a chemical equation, the state of matter of the chemicals may be shown as for solid, for liquid, and for gas. An aqueous solution is denoted. Matter in the plasma state is seldom used in chemical equations, so there is no standard symbol to denote it. In the rare equations that plasma is used in, plasma is symbolized as non-classical states. Glass is a non-crystalline or amorphous solid material that exhibits a glass transition when heated towards the liquid state. Glasses can be made of quite different classes of materials. Inorganic networks, metallic alloys, ionic melts, aqueous solutions, molecular liquids, and polymers. Thermodynamically, a glass is in a metastable state with respect to its crystalline counterpart. The conversion rate, however, is practically zero. Crystals with some degree of disorder. A plastic crystal is a molecular solid with long-range positional order but with constituent molecules retaining rotational freedom. In an orientational glass, this degree of freedom is frozen in a quenched disordered state. Similarly, in a spin glass, magnetic disorder is frozen. Liquid crystal states. Liquid crystal states have properties intermediate between mobile liquids and ordered solids. Generally, they are able to flow like a liquid, but exhibiting long-range order. For example, the nematic phase consists of long rod-like molecules such as para-azoxyanisole, which is nematic in the temperature range 118 to 136 degrees Celsius. In this state, the molecules flow as in a liquid, but they all point in the same direction and cannot rotate freely. Other types of liquid crystals are described in the main article on these states. Several types have technological importance. For example, in liquid crystal displays, magnetically ordered transition metal atoms often have magnetic moments due to the net spin of electrons that remain unpaired and do not form chemical bonds. In some solids, the magnetic moments on different atoms are ordered and can form a ferromagnet, an antiferromagnet, or a ferrimagnet. In a ferromagnet, for instance, solid iron, the magnetic moment on each atom is aligned in the same direction. If the domains are also aligned, the solid is a permanent magnet, which is magnetic even in the absence of an external magnetic field. The magnetization disappears when the magnet is heated to the Curie point, which for iron is 768 degrees Celsius. An antiferromagnet has two networks of equal and opposite magnetic moments, which cancel each other out so that the net magnetization is zero. For example, in nickel oxide, half the nickel atoms have moments aligned in one direction and half in the opposite direction. In a ferrimagnet, the two networks of magnetic moments are opposite but unequal, so that cancellation is incomplete and there is a non-zero net magnetization. An example is magnetite, which contains Fe2+ and Fe3+ ions with different magnetic moments. Microphase-separated copolymers can undergo microphase separation to form a diverse array of periodic nanostructures, as shown in the example of the styrene-butadiene-styrene block copolymer shown at right. Microphase separation can be understood by analogy to the phase separation between oil and water. Due to chemical incompatibility between the blocks, block copolymers undergo a similar phase separation. However, because the blocks are covalently bonded to each other, they cannot demix macroscopically as water and oil can, and so instead the blocks form nanometer-sized structures. Depending on the relative lengths of each block and the overall block topology of the polymers, many morphologies can be obtained, each its own phase of matter. Quantum spin liquid, a disordered state in a system of interacting quantum spins which preserves its disorder to very low temperatures. Unlike other disordered states, low-temperature states, superfluid close to absolute zero, some liquids form a second liquid state described as superfluid because it has zero viscosity. This was discovered in 1937 for helium, which forms a superfluid below the lambda temperature of 2.17 K. In this state it will attempt to climb out of its container. It also has infinite thermal conductivity so that no temperature gradient can form in a superfluid. Placing a superfluid in a spinning container will result in quantized vortices. These properties are explained by the theory that the common isotope helium-4 forms a Bose-Einstein condensate in the superfluid state. More recently, fermionic condensate superfluids have been formed at even lower temperatures by the rare isotope helium-3 and by lithium-6. Bose-Einstein condensate. In 1924, Albert Einstein and Satyendranath Bose predicted the Bose-Einstein condensate, sometimes referred to as the fifth state of matter. In a Beck, matter stops behaving as independent particles, and collapses into a single quantum state that can be described with a single, uniform wave function. In the gas phase, the Bose-Einstein condensate remained an unverified theoretical prediction for many years. In 1995, the research groups of Eric Cornell and Carl Wieman, of JILA at the University of Colorado at Boulder, produced the first such condensate experimentally. A Bose-Einstein condensate is colder than a solid. It may occur when atoms have very similar quantum levels, at temperatures very close to absolute zero. Fermionic condensate. A fermionic condensate is similar to the Bose-Einstein condensate but composed of fermions. The Pauli exclusion principle prevents fermions from entering the same quantum state, but a pair of fermions can behave as a boson, and multiple such pairs can then enter the same quantum state without restriction. Rydberg molecule. One of the metastable states of strongly non-ideal plasma is Rydberg matter, which forms upon condensation of excited atoms. These atoms can also turn into ions and electrons if they reach a certain temperature. In April 2009, Nature reported the creation of Rydberg molecules from a Rydberg atom and a ground state atom, confirming that such a state of matter could exist. The experiment was performed using ultracold rubidium atoms. Quantum Hall state. A quantum Hall state gives rise to quantized Hall voltage measured in the direction perpendicular to the current flow. A quantum spin Hall state is a theoretical phase that may pave the way for the development of electronic devices that dissipate less energy and generate less heat. This is a derivation of the quantum Hall state of matter. Strange matter. Strange matter is a type of quark matter that may exist inside some neutron stars close to the Tolman-Oppenheimer-Volkoff limit. It may be stable at lower energy states once formed. Photonic matter. In photonic matter, photons behave as if they had mass, and can interact with each other, even forming photonic molecules. This is in contrast to the usual properties of photons, which have no rest mass, and cannot interact. Droplet. A quantum fog of electrons and holes that flow around each other and even ripple like a liquid, rather than existing as discrete pairs. High energy states. Degenerate matter under extremely high pressure. Ordinary matter undergoes a transition to a series of exotic states of matter collectively known as degenerate matter. In these conditions, the structure of matter is supported by the Pauli exclusion principle. These are of great interest to astrophysicists, because these high-pressure conditions are believed to exist inside stars that have used up to their nuclear fusion fuel, such as the white dwarfs and neutron stars. Electron degenerate matter is found inside white dwarf stars. Electrons remain bound to atoms but are able to transfer to adjacent atoms. Neutron degenerate matter is found in neutron stars. Vast gravitational pressure compresses atoms so strongly that the electrons are forced to combine with protons via inverse beta decay, resulting in a superdense conglomeration of neutrons. Quark-gluon plasma. Quark-gluon plasma is a phase in which quarks become free and able to move independently in a sea of gluons. This is similar to splitting molecules into atoms. This state may be briefly attainable in particle accelerators, and allows scientists to observe the properties of individual quarks, and not just theorize. See also strangeness production. Quark-gluon plasma was discovered at CERN in 2000. Color glass condensate. Color glass condensate is a type of matter theorized to exist in atomic nuclei traveling near the speed of light. According to Einstein's theory of relativity, a high-energy nucleus appears length contracted, or compressed, along its direction of motion. As a result, the gluons inside the nucleus appear to a stationary observer as a gluonic wall, traveling near the speed of light. At very high energies, the density of the gluons in this wall is seen to increase greatly. Unlike the quark-gluon plasma produced in the collision of such walls, the color glass condensate describes the walls themselves, and is an intrinsic property of the particles that can only be observed under high-energy conditions such as those at RHIC and possibly at the Large Hadron Collider as well. Very high-energy states. The gravitational singularity predicted by general relativity to exist at the center of a black hole is not a phase of matter. It is not a material object at all but rather a property of space-time at a location. It could be argued, of course, that all particles are properties of space-time at a location, leaving a half-note of controversy on the subject.